So here we'll talk about angle of acceptance, which is the maximum angle at which light ray can enter inside the optical fiber so that it will propagate throughout the optical fiber based on the principle of total internal reflection. Now we'll derive a relation for angle of acceptance and numerical aperture. Let's have a look. On this diagram, here we can see that this is an optical fiber, this is the core area, this is cladding part. Refractive index of core is N1, refractive index of cladding is N2, and refractive index of air is N0. Here we can see a light ray which is entering inside the optical fiber. So this is the point of incidence, and because light ray is traveling from air to glass, it will undergo refraction first and it will bend towards the normal. So this is angle of incidence and this is angle of refraction. So here, because light ray is traveling from denser medium to rarer medium, angle of refraction will be lesser than angle of incidence. And we'll write Snell's law for this point, and Snell's law is sin I over sin R is equal to refractive index. So because light ray is traveling from air to glass, so refractive index of glass, which is N1 divided by refractive index of air. Now at the place of I we'll have to write theta naught, and at the place of R we'll have to write theta 1. So if we'll place these values and if we'll cross multiply, we'll get this equation. Okay, now if we'll talk about this ray which is striking the core cladding interface, and because this angle is theta I, this will also be theta I, and it is going parallel to the normal. So it is making 90-degree angle with the normal at point B. So here in this case, angle of incidence will be theta 1 and angle of refraction will be 90 degrees. So instead of writing theta 1, we'll have to take angle with normal, and we don't know the value of this angle, but we know that this whole is 90 degrees and this is theta 1. So this will be 90 minus theta 1. So we'll write Snell's law for point B again. It will be N1 sin 90 minus theta 1 is equal to N2 sin 90. N1 and N2 because light ray is traveling from the medium of refractive index N1 to the medium of refractive index N2. Now because sin 90 minus theta is cos theta, so we'll write cos theta 1 here, and sin 90 is 1. So N1 cos theta 1 is equal to N2. So we'll get the value of cos theta 1, which is N2 divided by N1. Now from equation 1, when we'll rewrite this equation, we'll get the value of sin theta naught, which will be N1 divided by N0 is equal to sin theta 1. Now we want to change this sin theta 1 into cos theta 1, and we'll use this formula sin theta 1 is equal to square root of 1 minus cos square theta 1, which is a mathematical formula. And after this, because we have value of cos theta 1, we'll place this value here, and because it is a square, so we'll get N2 square divided by N1 square. And when we'll solve this, we'll get square root of N1 square minus N2 square divided by N0. Now what is N0? N0 is the refractive index of air, which is 1. So we can write sin theta naught is equal to square root of N1 square minus N2 square. And sin theta naught is nothing but numerical aperture. So we can write numerical aperture is equal to N1 square minus N2 square. Now here we can see that To satisfy the condition of total internal reflection, theta 1 should be less than theta naught. So, whatever angle with which light ray will enter inside the optical fiber, theta naught is the maximum acceptance angle. So, our angle should be either less or equal to theta naught. So, we'll consider it as theta I. So, angle of incidence should be lesser than theta naught for best results, because when angle of acceptance is equal to theta naught, light ray is not coming back into the same medium, but it is moving parallel to the normal, and we want light ray to come back into the same medium, so it should be lesser. Now we'll say sine, we'll take sine, so sine theta I lesser than sine theta naught. Now the value of sine theta naught is square root of n1 square minus n2 square. So sine theta I should be lesser than n1 square minus n2 square, which is what? Numerical aperture. So we can also write sine theta I should be lesser than numerical aperture. This is the condition for angle of acceptance and numerical aperture. Now there is one term, fractional index change. Now what is that? It is the ratio of refractive index difference between the core and cladding to the refractive index of the core of an optical fiber. So just now we have seen that the refractive index of core was N1 and refractive index of cladding was N2. So difference between their refractive indices, which is N1 minus N2. So we'll write N1 minus N2 because N1 is always bigger than N2. So we cannot write N2 minus N1 here, divided by the refractive index of core, which is N1. So N1 minus N2 divided by N1 is known as fractional index change, and when we denote it by delta. They can ask a numerical based on this formula. The next thing is relation between numerical aperture and fractional refractive index. So this is the formula for fractional refractive index. Delta is equal to n1 minus n2 divided by n1, and we can cross multiply it to get this equation. Now we know that the formula for numerical aperture is square root of n1 square minus n2 square. Now what we can do is we can use the formula of a square minus b square to open this, and we'll get a plus b, a minus b, which is n1 plus n2, n1 minus n2. Now if we'll consider refractive indices are almost same, which means n1 is equivalent to n2, then what we can do is we can place n1 is equal to n2. So wherever we have n2, we'll write n1. So when we'll do this here, we'll get n1 plus n1 twice of n1, and the value of n1 minus n2 is delta n1 from here. So twice of n1 multiplied by delta n1 inside square root, which is equal to twice of n1 square delta inside square root. So this is the value we'll get. Now because we have square of n1 square, so we can take n1 square outside the square root, we'll get n1 square root of twice of delta. So this is the relation between numerical aperture and fractional refractive index. Here, from here we can see that numerical aperture depends on delta. As the delta increases, value of numerical aperture increases. That's all.